자, 그러면 지난 시간에 이어서 계속 할게요. 지난 시간에 본 게 어떤 것이었죠? 그래서 어떤 식으로 이제 프라이싱이 이루어지는지, 그리고 특히 마켓이 컴플릿 할 때, 컴플릿 마켓 상황에서 어떤 식으로 스토캐스틱 디스카운트 팩터가 얻어지는지 봤잖아요. 즉, 프라이싱이 어떤 식으로 결정되는지를 봤습니다. 그런데 아직도 약간 인투이티브하지 않아요. 그래서 조금 더 인투이티브한 세팅으로 바꾸고 거기서 나오는 개념이 리스크 뉴트럴 프로버빌리티라는 개념이거든요. 자, 그러면 이제 리스크 뉴트럴 프로버빌리티로 어떤 식으로 프라이싱을 해석할 수 있고 프라이싱이 어떻게 되는지 보겠습니다. Now, continuing on what we learned last time, we will link stochastic discount factor into risk neutral probabilities. Then the pricing becomes a little bit more intuitive. So as we've seen in the previous class, pricing in general can be represented as the expectation of m times x, right? So here m is the usual stochastic discount factor. Okay, so the m is the usual stochastic discount factor. And now we have the complete market. The benefit of the complete market is we can express it in terms of individual states. Right? 그래서 이렇게 probability of the state times the stochastic discount factor and the payoff, right? So that is simply the expectation of m times x. 자, 이게 그러면 m 곱하기 x의 expectation이 되고요. Now, we want to convert it into the usual discounted expected cash flow setting. So how do we do that? We will just divide and multiply the same thing. We will divide by the risk-free rate and multiply inside. Then mathematically they are the same. 자, 좀 더 인투이티브한 폼으로 바꾸기 위해서 제일 인투이티브한 프라이싱이 어떤 거죠? 바로 디스카운트 레이스로 나눠주는 거잖아요. 나눠주고 기대 수익률을 곱해주는 거. 따라서 우리가 디스카운트 레이스로 나눠줍니다. We will use the risk-free rate. So we divide risk-free rate and multiply it back. And then we get the following. Now, we can rewrite it by calling this thing as a new probability measures. So instead of, so previously, the real probability of each state, remember the very first example that we saw? 제일 첫 번째 시간에서 이런 example들을 봤잖아요. 그래서 각 스테이트에 대해서 the first state was the good state, the second state is the normal state, and the last state is the bad state. 각 스테이트에 대해서 이렇게 probability가 실제 physical한 probability가 주어졌어요. These probabilities are the real probabilities of the three states, or at least the probabilities that the agents believe will occur in the future. Okay? 자, 그런데 이 probability를 쓰는 게 아니라 we're not using this set of probabilities any longer, but we will come up with a new set of probability, which we'll call the new probability measures. Okay? And the pricing becomes as if we are using this new set of probabilities instead of pi. Okay? 자, 이게 제일 중요한 컨셉 중 하나예요. 컴플릿 마켓 아니면 에셋 프라이싱 티오리 시간에서 가르치는 제일 중요한 컨셉입니다. 즉, 프라이싱을 할 때 보통 이제 프라이싱이 discounted expected future cash flow라 그러잖아요. 즉, 미래의 기대 수익률을 디스카운팅을 해야 되는데 디스카운팅을 만약에 리스크 프리 레이트로 한다는 것까지는 괜찮아요. 디스카운팅을 리스크 프리 레이트로 하는 건 괜찮습니다. But when you take the expectation, you should never use the usual physical probability. You should use instead what's called the stochastic discount factor. I'm sorry, the risk neutral probabilities. Okay? In other words, now the pricing becomes discounted expected cash flows with respect to the new probability measure. Again, when you say pricing is the same as the discounted expected cash flows, and when you use the risk-free rate as the discount rate, the expectation on the cash flows shouldn't be calculated based on the real probabilities. It should be calculated instead based on what is called the risk-neutral probabilities. Okay? And you can actually prove it that risk-neutral probabilities sum up to 1. In other words, if you sum risk-free, risk-neutral probabilities across S, where MS is the and you can actually prove that the sum of the risk-neutral probability is simply 1. Okay. 그리고 다음 것도 보여줄 수 있어요. Risk-free rate is simply 1 over sum of all contingent claims. Why? Because risk-free rate pays 1 in all the states. So simply risk-free asset pays 1 in all the states. So simply the price of this risk-free asset is basically sum of all contingent claims, right? Therefore, the risk-free rate is 1 over the price, and the price is sum of the all possible states. And that is basically the same as 1 over expected value of the stochastic discount factor. Why? Expected value of the stochastic discount factor is basically sum of, okay, sum of ones across all states multiplied by the stochastic discount factor, meaning that this is just the asset that pays 1 in all the states. So you can actually prove it. The risk-free rate is given as the 1 over expected value of M, which is basically the same as what we saw in the very first case, in the very first class. 따라서 이제 리스크 뉴트럴, 우리 같은 세팅에서 risk-free rate은 1 over expected value of M, 즉 expected value of M 분의 1 같은 형식을 띠게 됩니다. Now, the risk-neutral pricing means that one can price assets as if all agents are risk-neutral, but with probabilities pi star instead of true probability. 무슨 말이냐? risk-neutral pricing이란 말은 우리가 expectation을 취하긴 하고 discount rate으로 나눠주잖아요. But the fact that we can use the risk-free rate as the discount rate, risk-free rate를 discount rate로 쓸 수 있기 때문에 즉 무슨 말이냐 하면 인베스터가 리스크 뉴트럴한 거와 다름이 없다고 가정을 하고 한 프라이싱과 똑같이 나오게 되는 겁니다. That's the reason why it's called the risk-neutral pricing and risk-neutral probabilities. And an important property is that risk-neutral probabilities give greater weight to states with higher marginal utility. High marginal utility가 어떤 state이죠? High marginal utility state is a bad state of the world. Okay? How can you see that? The risk-neutral probability is basically RF, risk-free rate times risk-free rate times the stochastic discount factor, right? Therefore, because the stochastic discount factor is countercyclical. When things are bad, stochastic discount factor is high. When things are good, stochastic discount factor is low. Okay? Therefore, risk-neutral probability has the same property. It gives more probability on the best state of the world. Okay? So it's the same intuition as the previous consumption-based stochastic discount factor, where the stochastic discount factor was given as like this, right? Okay? 어떻게 보면 되게 인투이티브한 결과예요. 여러분들이 프라이싱 할 때는 bad state of the world에 더 포커스를 해야 되는 겁니다. 왜? 그 스테이시 여러분들이 마지노 유틸리티가 높고 그 스테이트에 인슈런스 베네핏을 주는 에셋들에 대해서 가격이 더 높은 거예요. 즉 금과 같은 에셋이 why is gold so expensive? Because gold pays off when things are bad. Therefore, investors want to pay more. That's one way to understand the pricing of gold. We can also write risk-neutral probability in this fashion, where the ratio between stochastic discount factor and expected value of the stochastic discount factor is sometimes called Radon-Nikodym derivative.